Hello. Welcome to the Senior Design Showcase submission for the Optical Beacon Tracker for Optical Wireless Communication by Group 4 and sponsored by the Night Vision Lab. Group 4 is comprised of myself, Seth Johnson, the photonic science engineer,
Blake Baez, computer engineering,
and Raymond Loudis, electrical engineering.
Our sponsor, the Night Vision Lab, is a research group at Creel with projects in fields such as metasurface aberration correctors, vision-based navigation, sensing technologies from small UASs, and wireless optical communications. The reason we chose this project is so that way we can help advance the progress of optical wireless communications by one small step. Optical wireless communications are not a new concept by any means. However, maintaining wireless communications via a laser or an LED is very difficult and requires very precise alignment. And maintaining the alignment while mobile is even more difficult. So we will be building a device that can maintain that accuracy for communications. The overall project will comprise of two parts, the receiver and then the beacon. The receiver will have various photodetectors, including a quadrant photodiode and a single cell photodiode, motors, and its own optical design. The beacon system will comprise of the output of a fiber laser, an array of LEDs, more optical design, and other motors. Both will be equipped with GPS, LoRa, and IMU modules, and must be accurate within a percentage of a degree. To accomplish our goals and objectives and finish this project, work will have to be distributed as so. As the photonic science engineer, I will be in charge of the optical design or optoelectronic hardware selection, and I will also assist in physically assembling the beacon and the receiver along with Raymond. The optical design includes collimating our array and matching the output divergence to our fiber laser, and then on the receiver side, we must focus the light into a fiber cable while also maintaining a large spot size to hit our quadrant photodiode.
As a computer engineer, I will be in charge of the software design. I was also in charge of the MCU, GPS, LoRa, and IMU selection. I also designed and maintained the website for this project, as well as calibrated all our modules for the prototypes.
As the electrical engineer, I'll be responsible for the PCB design, power distribution, and physically assembling the beacon and receiver along with Seth. During the design process of our PCBs, we got some very valuable feedback from our reviewers and other faculty members. One piece of advice that proved helpful was to use very large trace widths in order to troubleshoot, in case we had to cut and get to the trace and make modifications while we prototype. Another piece of advice that we adhered to was to use only 2-layer boards. Using multiple layers can lead to capacitance within your board, which will interfere with some of the ICs and circuitry on different levels.
Another valuable piece of information that we got was to use dual power meters for measuring divergence. An important specification for our project is the output divergence of our beacon. A normal way for measuring the divergence is to simply take pictures of your beam at different distances and then measuring the width. However, when we're working with infrared wavelengths, such as we are, taking pictures can be rather difficult. So a piece of advice that we received was to use two power meters and then place them at specific distances apart from each other in order to measure the divergence of the beam.
Another big piece of advice we got was to use debugging LEDs where possible. Such places included our breadboards, PCB designs, and any modules that proved suitable. Using debug LEDs allowed us to break down and pinpoint any potential errors we could have had, and it saved us a lot of time.
Currently, we are still in our prototype phase, as we continue to work on structural integrity and wire management, but all of our modules and hardware have been tested individually and have assured us that our specs can and will be met for our live demo later this week. On the left is our receiver prototype, equipped with a quad cell photodiode. The saturation on each of the quadrants will determine whether or not the device needs to turn left, right, up, or down. In order to achieve these movements, we are using servo motors, which are controlled by an ESP32S3 Mini. Currently, we are using GPS and IMU data to align the beacon and the receiver roughly, while we're relying on our optics to refine that alignment in order to have optical communication. On the right side is our beacon, which is equipped with
On the right side of our beacon is we have some of the most heavy optical design, which includes an array of LEDs, which serves as our beacon, the output of a fiber laser, which would serve as our mock communicator, and then various other optical components such as diffusers, dichroic mirrors, and uh, diverging lenses.
For both the transmitter and receiver, there are two motors. Both have been highly calibrated within to a fraction of a degree. They both have IMUs, which have also been calibrated and cross-checked with other compasses, as well as LoRa modules that have been fine-tuned.
With our motivations in mind, the goals of this project are for us to create a beacon with enough power and divergence to be detected up to 3 meters away while indoors, and we should create a receiver that can actively track that beacon while mobile up to 3 meters away. An advanced goal is to track the beacon up to 1 kilometer away while outdoors, and our stretch goal is to track up to 10 kilometers away and be able to transmit and decode a simple signal. It should be stressed that we are not building an actual communicator, we're simply building the device to assist with communications.